Dear students, I hope you are well and doing your homeworks, studying and learning physics day by day. In this situation of coronavirus epidemic, we don't have any other way to conduct classes. The government and then UGC has ordered us to take classes online. Yes, if we get time after the epidemic goes away, we should repeat these classes, but in brief. For the time being, I am going to give you all possible lectures to complete the course. Today I shall discuss about potential energy and subsequent methods. You already know what is kinetic energy. Kinetic energy is energy of motion. There is another kind of energy which is potential energy. And potential energy is called the energy of configuration. What is configuration? In brief and in short words, configuration is the way the bodies, the equipments, the parts are arranged in a system. Say I have a square and I have 4 electrons. I can put 1 electron in each corner. So I have a square and on each corner of this square there is a electrical particle. Now every two particles will interact. In this way, interaction energy will give us an energy. That energy is potential energy. Okay, let's take another example. I have a great system, say galaxy. In a galaxy there are about 10,000 stars. Yes? So these stars interact via gravitational force. So this force gives interaction and interaction gives them energy. That energy is energy of potential or potential energy. So that mechanical energy are of two kinds, kinetic energy and potential energy. Kinetic energy is energy of motion, potential energy is energy of configuration. So I have a complex system. There are many parts and some work is done on that system. I am repeating. I have a system. The system is complex. It has many parts. Now some work done by external agent on the system. In this way, the potential energy, initial potential energy Ui will change to final potential energy UF. So what will be the change? The change in potential energy. The change in potential energy. The change in potential energy is delta U. This is just a symbol. This says that it is the change in energy. What energy? U. U is what? Potential energy. The symbol U is used for potential energy. Sometimes in electrostatics, the symbol V is also used. So UV, these are two letters used for potential energy. Here we use U. delta U is what? The change in potential energy. And I have told you in a previous class, students always do a problem. What problem? They subtract the final energy from the initial energy to get the change. No, that's not the actual way. Actually, you have to subtract the initial energy from the final energy. So then U is nothing but UF minus UI. Then U is UF plus UI. How this come about? Because the system is complex and external agent do some work on the system. Due to that work, the potential energy changes from UI to UF. Now we postulate that it is not necessary from science or physics, but it is a concept. Conceptually it is required. It is required by concept that we write this change is equal to minus W. What is W? W is the work done on the system for which the initial potential energy is UI and it has changed to UF due to the work done on the system. Yes, you understand this. This is simple physics. There is nothing hard, nothing tough in this situation. There is nothing hard. Now say we are shifting our standpoint from complex system to a single particle system. Let I have a single particle and it is moving along the x direction. In other words, it is confined in the x direction. It is confined in the x direction. So, what will be if W work is done? If W work is done, what will be the change in del U say the initial position? Let me write it. Let a single particle is at xi and work W is done on it and the final location is xf. By definition, del U is U of xf minus U of I, right? U f of x, U I. You don't need to write this f. You don't need to write this U of x, right? This is the change in potential energy. Now, what is del U? Here, come here. Del U is minus W. And we have already encountered the definition of W. What is W? W is given by the if initial is xi, final is xf. W is given by xi to xf f of x function of x dx. Right? This formula is discussed before. W in one-dimensional motion is given by the integral xi to xf f of x function of x dx. Now, what about the minus sign? This is only W, so you have to put the minus sign. So, del u is given by minus integral 1 f of x dx, and the limits are xi to xf. Xi to xf. Okay? Okay. Now, you might know that whenever we calculate potential energy of a particle in the field of Earth, we take the Earth's surface as zero potential, right? You know this. You have understood. You have learned this in your intermediate classes. That means there are many situations. In all situations, we can take an arbitrary point as a reference point and assign a particular potential to that point, and then with respect to that we find the potential energy at a particular point. Say the reference point is x0 and we want to know the u. Say the reference point is x0 and we want to know the u, that is potential at x. Then what we will find? You will find u of x minus u of x0 equals minus f of x dx x0 to x. Right? This is the formula. Now comes the important part. My question is, I have a system and I want to know the potential energy at a particular situation, at a particular, for a single particle at a particular location. And the reference point is, say, x equal 5 in some unit, meter, centimeter, anything. You have fixed your reference point, and then you find the potential at another point with respect to that point. Now you shift the reference point. Say now it is 3. The location is different, the potential at that position is different, and with respect to that, you again calculate the potential. Okay, you have done two things. But this does not matter. Whether you choose the reference point at 3 or 5, what matters is the difference between the initial and the final potential energy. That means the meaningful quantity is here delta u. Delta u is a meaningful quantity. Delta u. That means you want to know u of x2 minus u of x1. It is important. This is important. Say I have a particle moving in the x direction. I want to find, my question will be, what is the difference between potentiality between x equal to 5 and x equal to 10? Or what will be the difference in potentiality between x equal to 15 and x equal to 100? That is the actual question. What is the difference between two potential energy between two arbitrary points? The reference point will go away. Reference point is only important in first derivation, in the first principle. I shall elaborate this thing a little bit so that you understand what I say is really correct. You can change this x naught. You can change this x naught, but then between 2 points the potential energy does not differ. Say we choose a point as reference point and assign 5 units for the potential. Okay, I choose a point and assign x equal to u of x naught. U of x naught is equals 5. In this formula, u of x naught equals 5. Now, say we want to find u of x1 minus u of x1, x2 is arbitrary. x1, x2 arbitrary, can be any 2 points. x1, x2 can be any 2 points. Okay, first find u of x1. U of x1 here, from here, u of x1. Right hand x1, this is fixed because this is the reference point. Once you have chosen the reference point, it is fixed for the calculation of the right moment. Okay, then what will be u of x1 minus x naught to x f of x dx plus of 5. Right? Okay. What is u of x2 minus x naught? This is one. This is x1. This is x2. F of x dx plus of 5. In both formula, minus of 5 gone into the right hand side. Right. Now you calculate u of x1 minus u of x2. What will do that? From that formulas, u of x1 minus 5. Now I have x naught equals 5. No, not 5 here. This is x naught. This is x naught. This is x naught to x1 f of x dx plus 5 plus x2 to the kilogram. What will we write for x2? Minus plus x naught to x2 f of x dx plus of 5. Next, I elaborate this. Say I have done the integration. Say I have done the integration. So what I'll find? I'll find minus integration x naught to x1 f of x dx x naught to x1. Right? I have done the integration. So integration is done. Actually, it is not done numerically. Numerically, we have not done, but analytically, we have finished. Analytically, we have done the integration, and I am putting the limits. Plus of x naught to x2 f of x to x dx x naught to x2. Now expand this. What you will find? Minus integration. You have to put this on this integral. You have to put x1 and x0. So you will write limit integration f of x x dx. It is for what? x1. Minus plus integration f of x dx. The point is x0. For the next, plus f of x dx. The point is x2. Minus integration f of x dx x0. There is a minus sign. These two terms same cancels. What you find now is equals integration f of x dx of what? x2 minus f of x dx x1. Okay. So this is a number. This is number integration and number of the integration at x2. It is at x1. So I have f of x dx x1 to x2. What we have started with u of x1 minus u of x2. Now by definition it is minus w. By definition minus w. And there will be a minus sign here. U of x1 will be the upper. x2 will be the minus. What is that? Minus. U of x1 minus u of x2 equals minus w. U of x1 minus u of x2 equals minus w. What is w? x2 to x1 f of x is this. Because always w is between two limits. Here the limits are x2 to x1. So the difference of u will be u of x1 minus u of x2 is equals this thing equals minus w. So either you put or use number for a reference point and keep it along your calculation, though that number does not affect your final calculation, which is what? The difference in potential energy between 2 points. We have for a single particle, compare this, for a single particle we have write U of XL minus U of X naught equals minus W. What is W? What is W between X and XL? X naught XL F of X is right. You have X, U accept plus U accept equals by W. What is W? Accept to accept, above J. So finished. This is the explanation. This is the explanation of potential energy related to the reference point. You can change your reference point at any time, but in a single calculation, you should keep it fixed. For another calculation, you can use another reference point, and you will find the same difference of the potential energy between 2 points. If you shift the reference point, the final result, which is the potential difference between 2 points, does not change. Okay, now we come to an important point. I have what? I have what? U of X minus U of X naught equals minus X naught to X F of X dx. Okay. Differentiate this whole. Differentiate this. What will you find? D of U X by dx. Differentiate it just with X. It is a reference point. It is a fixed constant. From here you will find 0. Now here what? The minus sign remains, and this is an integral. The differential of an integral is the same thing. Differential of the integral is the integrand. Understand? Deeply understand. The differential of an integral is the integrand. What is integrand? Here the integrand is this. You omit the d term, you omit the dx, dz term. The remaining thing is integrand. That means of which the integration is being done. So minus and remains. You differentiate this, you will get what? F of x. Of x. Or you can write also just like this. So f of x is du by dx. The important formula. Once you have the potential energy, you know the force, what is acting on the system. Once you know the potential energy as a function of x, you know the force acting on the system. Right? That means that there are two things. The minus sign. You have to have a minus sign here. I forgot the first place. I forgot the first place, minus sign. So negative of the differential of u gives you the force. negative of the differential of the force gives you the F. So much for potential energy. We now shift to an important law of nature which is called conservation of energy. We shall now consider conservation of energy. What is conservation? Whenever something is not lost, what is before and after some process, the same thing remains, we call it is a conservation of that thing. That means nothing is lost. If something is lost, then it is not conserved. If something is not lost, it is conserved. Right? Say, we shall use an example to elaborate this point of conservation of energy. Say, here is the wall with which a spring is attached with a block, spring. Here it is some distance. This is the x direction. Here it is x equals d. Here it is x equals 0. Okay. Say the relaxed position is 0, right? Relaxed position is 0. That means when there is no work, there is no force on the block. The block is relaxed at x equals 0. Some external agent pushed it up to this point. Then she suddenly withdraws his force. The spring will what do? The spring will expand. So say I begin calculating not from the beginning but from here. From x equal to t. The spring is expanding again, expanding, comes back to x equals 0. Comes after x equals 0. So we shall consider here the spring is working, right? The spring is working. Here it has only potential energy because the force is forcing it, acting it to remain, to fix it at this position. So the spring has only potential energy. It does not have any kinetic energy. Let go of the external agent, it will expand. What it will gain? It will gain kinetic energy. So what will be the kinetic energy? Del K, the change in kinetic energy, equals what? W. What is W? W is the work the spring does on this block. What is W? W is the work the spring is doing on the block. It is pushing the block up to this point. So the spring does work, right? The spring does work. The spring does work. So it works so that the work done is the change in kinetic energy of the block. The work done on the block is equal to the change in kinetic energy of the block. Okay. What will happen to the potential energy? In this position, any layman will say the potential is maximum because it is highly compressed, and in this position it is relaxed. So if it is energy, here the energy will be maximum, here the energy will be minimum. In other words, whenever the spring expands, potential energy decreases. So we can write del U plus minus del W. This is our formula. These are nothing. We have encountered this before. Just a little bit ago. These are the formulas. Del K is W. This is the last lecture. Half mv I square is subtracted from half mv f square, which is equal to W. And today we have learned potential energy difference is nothing but the negative of the work done. Okay. So what we can do now? We can write del K, W is minus W, del K minus del U. Del K equals minus delta U, right? Here, for W, you write minus W. Then you can write delta K plus delta U equals 0. Then you can write delta K plus U equals 0. Here comes the concept of mechanical energy. Mechanical energy has only two parts. One is kinetic energy, another is potential energy. Kinetic and potential energy combinedly gives you the mechanical energy. Mechanical energy is mechanical energy is E equals K plus U. So that formula becomes del E equals 0. Right? In other words, this equals del K plus U. Now come to the point. Whenever something does not change, del of that is 0, right? Whenever something does not change, delta of something, that thing is 0. E does not change, so delta of that is 0. So E is a conserved quantity. So you can write, so for a system of mechanical type, there are other systems, other than mechanical, other systems, but mechanical system has this EI equals E, right? Since del E equals 0, if I write EI the initial kinetic energy, EM the final kinetic energy, then this two will be the same because E does not change. E does not change. Del of that is 0. It does not change. So EI equals EM. Now I have this formula. What is EI? EI is KI plus UI. What is EF? KF plus UF. Right? You understood this? This is a very nice piece of physics. You have encountered also this before. Now we have done it in a little bit different way, and we enjoyed it. You have enjoyed it, right? Yeah? You have enjoyed it. Now come to the language, the text. We should write this conservation of energy in a text form. Conservation of mechanical energy in an integrated system in which only conservative forces act, the total mechanical energy remains I have covered conservative forces, right? I have covered conservative forces in my last lecture, right? You remember that? In the last lecture, we have covered conservative force. What happens in conservative force? In conservative force, what happens? In the round trip, the total work is 0. So here, say this is the point I, this is the point F. The particle is going here to here. So the particle starts from here, goes to here F, come back to F. Initial and final point is R. What will be done? Del U equal to 0. Because potential is also energy. And the initial and final points are same. Then what will be del U? 0. No change in potential energy. Potential energy will be same. Del U so will be minus W. In other words, W is 0. For what? When a round trip is done by a system, the work done is 0. For what kind of force? This is true. Conservative force. Only for conservative force, W is 0 for a round trip or a full cycle. So, potential energy you can define for only conservative forces. Then you find mechanical energy which has two parts, kinetic energy and potential energy. Potential and kinetic energy in total remains constant whenever the system is isolated and only conservative forces act. If conservative forces doesn't act, you cannot have the concept of potential. If conservative force is not working, you cannot have potential energy. The concept of potential energy breaks down if conservative force is not there. You have to have conservative force, then you can define potential energy. Then you can define conservation of mechanical energy. I hope you have understood what I have delivered today this much. Stay home, stay safe, and pray to Almighty so that the outbreak of coronavirus goes away immediately and we can come to the campus and do our works as usual. May Allah help us all. Thank you very much.